Sonar affects large marine mammals, as many of you all know from news seeing beachings after naval activities. But there's been a lack of study on small organisms that make up the base of the food chain in the ocean.
The purpose of this study is to determine the effect of low-frequency active sonar on Polymonides fluviceps, on the movement of Polymonides fluviceps.
So first we'll be talking about the background information, then we'll be looking into the experimental design, next the procedures, and the experimental results, and we'll analyze these results, and then we'll draw our conclusions.
Sonar stands for Sound, Navigation, and Ranging. It's found in marine mammals for hunting, and the Navy uses it for helping to track ships underwater. And it's used to determine surroundings for research vessels mapping the ocean floor as well. What happens is a sound pulse is sent out, and they read how long it takes for the sound to get back, and they can judge the distance. It's shown to cause beachings and cetaceans because it can mess up their internal sonar and throw off where they think they're going, and that's shown by these research.
Polymonides fluviceps, more commonly known as eastern ghost shrimp due to their translucent exoskeleton, are found mostly in coastal freshwater, estuaries, and marine ecosystems. They are common prey for many fish and live usually 1 to 2 years. Their diet, for the most part, consists of the feces of larger fish and the occasional small fish. There have been studies conducted using or on ghost shrimp. One of these being as cited above by Rosa et al. 2005, who looked at the environmental conditions needed for ghost shrimp and other decapods to live in estuaries. This is the anatomy of a ghost shrimp. 3 of the main parts to note are the cephalothorax and the abdomen. Because the ghost shrimp is translucent, with the naked eye, you can see the internal organs.
In this experiment, our group considered several methods for tracking movement. First, we looked at electronic tagging. However, we found this to be impractical for use in captivity, even though it is useful for tracking large populations in the wild. Next, we look at infrared beams. However, due to the translucent nature of the shrimp, there's no guarantee that they would break the beam if they crossed it. Next, we looked at water disturbance. However, the disturbance created by the movement of the shrimp may not be significant enough to trigger a sensor. Finally, we decided on observation and measurement. So we set up a video camera and measured the tanks. Ian will talk more about this later. We found 2 studies in our research that dealt with the tracking of movement. First, in the study by Lemaire, Shannon, Clark, and Cornelissen in 2009, we found that electronic tagging is not very practical for use in captivity. And next we looked at a study by McGinnis in 2008, which looked at the water disturbance created by mud shrimp, a relative of Polymonides fluviceps.
Our hypothesis was if the decibels of our sonar would increase, the movement of the ghost shrimp would increase as well. And we at 4 levels, 0 decibels, which is our control with no sound. We had 71 decibels, 76 decibels, and 80 decibels. Our dependent variable was the movement of the shrimp in centimeters. We used the centimeter ruler next to the tank in the camera, and one of our main constants was the frequency of the sonar at 250 hertz.
For this experiment, our group developed a device called the APOE, or the Aquatic Pulse Meter, to to administer sounds at a frequency of 250 Hz for 1.5 minutes every 24 hours at each of our 3 levels of 71 decibels, 76 decibels, and 80 decibels. Here you can see the schematics that we used for this device. First, in figure 6 here, you see the 71 decibel circuit, which consisted of a speaker, a 9-volt battery, and a 330 ohm resistor. Here in figure 7, you can see the 76 decibel circuit, which consisted of a speaker and a 9-volt battery. And here you can see the 80 decibel circuit, which consisted of a 9-volt battery, a speaker, and an LM386 amplifying jack. Here's a video of the A4 in action. You can hear it goes to the 80 decibel, the 76 decibel, and then the 71 decibel speaker.
Our tanks, our 4 tanks were set up roughly 5 inches away from each other, with the 8 fluid connected to the three tanks that we emitted sonar to and our control left wing. This is a short animation in showing what we've done. What we did is we inserted the speakers, who's connected to a pulley, in standard heavy kitchen Ziploc bags into the tanks, and then we set up a ruler measurement, and then set up a camera so that we could check our measurements later. And we did this with all 3 of the tanks. To get our data, what we did is we took the average movement in each tank, adding up all of the movement of every ghost shrimp in the tank, and then dividing it by the number of ghost shrimp in the tank. And we had that for each day, for the 6 days, and then compiled the average of those 6 days. And as you can see, we had a few outliers, such as the 21.1 decibel, and then in day 1, and then in day 6, the 12.43, the amount of movement, and the 2.83 in day 2.
Here are our experimental statistics for this experiment. To test the null hypothesis, we used an analysis of variance or an ANOVA test at the 0.05 alpha significance level. Our null hypothesis was that there would be no significant change in movement between the control group and the exposed group. We rejected the null hypothesis because F critical was less than F and our p-value was less than R.
Here's the graph of our data. As you can see, the data increased logarithmically. This is most likely due to the fact that decibels are a logarithmic scale, and so this is the data that we would be expecting with the alternative hypothesis. And we measured it using that.
In this experiment, the increase in movement in the shrimp was most likely caused by vibrations due to the sonar. However, at higher decibel levels, such as those used by the Navy, at 120 decibels to 240 decibels, these same vibrations could cause ruptures in connective tissues and membranes. The further research is clearly needed to determine these effects at these higher decibel levels, the effects over time, the effects on other organisms.
So we ended up supporting our alternative hypothesis due to the ANOVA test, and we have little correlation with outside research due to the lack of research on the sonar and small organisms, and there definitely needs to be further research in this area to either validate or disprove our results.
We'd like to thank our wonderful IBET teachers, Dr. Lucero, Mr. Lewis, and Ms. Henry, for their help, and we'd also like to thank our families for their encouragement. And this is our literature cited.
Thank you. Are there any questions?
How did you decide on those decibel levels?
Well, due to our research limitations, those were the different